Okay, so in today's lecture, we're going to introduce the very important notion of gradient descent. This is a iterative algorithm that solves the following problem. So let f be a function of n variables, scalar value function. We seek to find or to solve min f of x where again x is some n-dimensional vector. Okay, so if you took the first version of this class, Math 2421 with me, I introduced this with functions of one variable. But just in case you didn't, I'm going to start by showing you how gradient descent works with functions of one variable, and then we'll give the natural generalization to this case here. So the idea is that the derivative with respect to each of your variables is going to tell you the direction of the graph of the function, in a sense. So, for example, like if this is a graph of your function f, okay, well, and suppose we want to find a minimum value for this function, for example, maybe here, right? Then if we make a guess at a minimizer of that function, then we can evaluate the value of the function there. But then also we can take the first derivative, which will tell us the slope of this tangent line, right? And if the slope is positive, right, like it is right here, then that means if we move to the right, we'd be going up the function. But if we move to the left, then we'd be going down the function towards a minimizer, a local minimizer. So that's what we would do. We would make an initial guess here. So x naught is an initial guess. Okay. And then we would make a new guess as following. Your previous guess plus alpha times the derivative's value at your old guess. Okay, and here alpha is called your step size. Well, but oftentimes in machine learning literature, it's more common to call it your learning rate. Okay. So, and alpha is typically some small number, some ratio that you will choose based off of just experimental evidence. And we'll look at an example in a moment. So maybe we can run gradient descent on this function, which looks to be, I don't know. So this is like the parabola been moved over maybe 1 unit and raised by 1 unit. So that looks like that function there. And if we're trying to find a local minimizer, which happens to be a global minimizer of this function, let's make a guess that it's 10 or something. So initial guess, maybe 10, and maybe we can choose alpha to be like 0.02 or something like this. Okay. And we know what the actual answer is. We know that this function is minimized at x equals to 1. But suppose we didn't, we make this guess, and then we're going to apply this update rule to get closer to the local minimizer. So I don't want to work it out by hand, so I'm just going to pull up Python real fast and show you how this is going to work. So share my screen. Everyone can see my screen, hopefully. Okay, so I should have some. Let's make a new one. Okay. Okay, so do some plotting. Okay. And then what was our function? F of x equals to, say, return x minus 1.0 all squared plus. Okay. And so we can look at the plot of this, I suppose. So actually, I should be using NumPy. And I think to make a domain to plot this thing, what is the thing? Is it a range? -10, -10. Oh, np dot. Oh, where'd you go? Did it not fill anything? Oh, I just need to know what this function does. I always forget the names of these things. So start, stop, step. Okay. Okay, so it's just, I'm just making a domain to plug in for the plotting. Maybe like, so start, maybe like -4, stop, maybe 10 increments 1.0. And then let's see if this works. I'm getting my commands mixed up. Did it not run? No, okay. So it just made a domain for me. And then maybe okay, so we want to find this minimizer at 1. Okay, so we chose alpha to be 0.02, and then our very first guess, what did I pick it to be? 10. Okay. So, and then what is the derivative of our function? The derivative of our function, we can figure that out fairly easy. Just write it out. So what is it? 2 times x minus 1.0. So that's our derivative. Okay, so then let's use the update rule. So x1 is going to be equal to x naught minus alpha times df of x naught. Okay. And let's go ahead and look where the points started off. Actually, let's start at 9.0. So let's start at 9.0. Okay. So then we can look at these points. So x naught, and then f at x naught, and then just, so this is where we started, and then, okay. So this is our first point here, right? This is at x equals to 9, and then what is x1? X1 is, so that didn't move very far, right? We started at 9 and now we're at 8.68. So what about if instead of doing that, what about if we said maybe increase alpha to be 0.2? Okay, so let's see what happens if we do that. So see, the learning rate or the step length is, it's telling us how far to step really in the direction of descent, right? And if I didn't mention it clearly earlier, we're subtracting this value off because if the derivative is positive, we want to go negative. If the derivative is negative, we want to go to the right, go positive. So, okay. Maybe let's iterate this a few times now and see what happens. So say maybe x2 now is equal to x1 times alpha that. And yeah, I'm curious. Just one more step and see. So now we have x2. Okay. Now notice that we didn't go as far this time. Why is that? Well, the reason is that over here at 9, the slope of the tangent line was steeper than the slope of the tangent line here, right? So like what are the differences? So df of 9.0. So the slope was 16 at 9, right? And then at our x1, it was 9.6. So when we were subtracting off this value at x1, we didn't take as far as a step because the slope of the tangent line was less, right? And it looks like if I iterate this again, right, if I just like, that we're going to take even a smaller step. So let's just see what happens when we do this. Okay. So how far did we go now? See, because the slope of the tangent line is decreasing, right? We're slowing down. When we subtract off, we're not stepping as far. So how can I do this all in one go now? So let me see. Let's copy everything in this cell, and I'm just gonna put it down here. So instead of doing it like this, I'm gonna say capital X is equal to a list with that. And then you can write a for loop. So for underscore in range. I don't know how many times you want to iterate it. Maybe we'll do it like 20 times. We'll say x new is equal to our previous x minus alpha times the derivative of our previous x. And then after we make that, we just put it inside our x dot and x new. Okay. And because I want to look at the plot of this, I'm going to go ahead and do that. There. And then okay. Copy that. So scatter 1 f at there. Make a new one, and then once we do that, then plot it. Okay, hopefully everyone understands what's happening there. And you can see that they're starting to jumble up at the minimum. In fact, it's like, what does x look like? Yeah, we're converging to 1. You see that? Okay. So how would you, in general, how would you do this? What would be a stopping criteria? There's several ways that you can stop the algorithm besides just giving it a max iteration. You could look at when the function is getting sufficiently close, when the derivative is sufficiently close to 0, to being 0, you know that you're at a critical point, right? So you could say something like, while np dot, actually I think it's just absolute value. So while the absolute value of df of your most recent x, while that's greater than, I don't know, 0.0001 or something. So while that and you want a max iteration because you don't want it to run forever. So maybe something like set k is equal to 0. Okay, less than like 1,000 or something. You don't go too far. Okay, equals 1. And let's make all these the same color. Red, maybe make marker plus sign or something. And I wonder how many times it went. How many times did it update? 25 times before this was broken. Okay. So that is gradient descent. And depending on your choice of alpha, like let's see what happens if we make alpha like 4.2, a really big learning rate. Let's see what happens. Result too large. We were jumping around too much, right? So yeah, look at the crazy values that we were getting. We were hopping around way too much. That step size was so big that we were, see how big these numbers are getting? It was so big that it blew up basically. But if you make it back down to something reasonable, like maybe even 0.5, oh, it only went one time. That was really weird. With this perfect, I wonder why this step rate, we updated one time, and we landed precisely on the minimizer, the critical number. That was very surprising. Never had that happen before. Okay, so let's like this function is kind of special in that it's so simple. Maybe we can make a more interesting function. So maybe oh, did not want to do that. So maybe instead of this, we can have like a crazy like quartic function plus cubed minus 32 times x or something. I wonder what this even looks like. What does this function look like? There. It's kind of wonky, I suppose. But we can still run gradient descent and see what happens with it. So let's go ahead and do that. So I'm just going to copy this code here. I have no idea what the minimizers are. I think the minimizers look like x to be 0, actually. The next, no. Well, we also need to write down the derivative, so let's just do another df. So what is the derivative? Return 4 times x minus 1.0 all cubed plus 3x squared minus 32. So let's just see what happens. Result too large. Maybe let's make like a super, let's guess it like 2.0 or something, or no, maybe -4. Is that, and make our step rate really small. Okay, so you can see it, we were going this way, right? Right. So that's kind of neat, right? And I'm assuming that that's the minimizer right around there. I can check what is the derivative at our last entry. Yeah, it's tiny. That's got to be close to that critical value. Okay. Okay, so is everyone clear with how gradient descent works in with a function of one variable?
Yeah.
Okay, so now let's talk about the more general case. And as before, we're going to use a very simple function of two variables. There's something like, what do I do with my chart? Suppose we have something like xy. I don't want it too simple, but maybe like something like that. Okay, so this is that bowl shape that we talked about a while back. So we understand what the picture of that looks like. It's going to look So it's been like the center's been kind of moved a little bit this way and up a little bit, more or less. It's going to look something like that. And a minimizer for a multivariable function is can be determined by looking at the critical points, just like you did with functions of one variable. But now the critical points are in terms of both x and y instead of just x. So local minimizer for x, y, say it's not, why not, satisfies f of x naught comma y naught less than or equal to f of x y for all x, y in the domain of f. Or not for all x and y in some intervals around x naught and y naught. Okay, so for example, the local minimizer here would be x equals, so in this case, we know the answer. The answer would be positive 1, negative 1 would be a minimizer for this function. So, because there's a little, so like here's like x equals to 1, and then y is equal to negative 1 is like this way. That's where the center is at. I kind of drew it a little bit off. But how can we understand how gradient descent will work in this case? Well, as I mentioned before, we need to just fix one of the variables here and then vary the other one and see how it behaves. So for example, when x is equal to positive 1 or something, or maybe let's say when x is equal to like 2, then z is going to be equal, so 2 minus 1 is 1, plus y plus 1 squared, right? So really, this picture bothering me, I gotta read it out. X, y, z. All right, so if we fix x at 2, right, and now we're going to treat z as a function of just y, that is the function. So there's like minus 1 for y, so it's going to look like this. Y is 0, z is 1. So it's just that function. Here's z, here's y, and here's z, right? And that's what this function looks like. So if we were on here, right, just there alone on this line, and we made a guess like right here, then as before, we just evaluate the function and we take the derivative and we see that the derivative is positive, which means if we're going to go downhill, we need to go to the left, right? So we would do this, we would use the same technique as before. To minimize on that line there, on that curve, we would say that what are the variables here? So it's like yn plus 1 is going to be equal to yn plus some learning rate times the derivative of z with respect to y at yn. That's just another way of writing the gradient descent, right? And we make another guess here, so forth and so on. But there's more dimensionality to this, right? Because there's also a curve like this. So this is for the variable x now. So this is in so that's when maybe y can be fixed at say +1, and then z would be equal to -1 squared plus 2 plus 4. This is like on this axis would been raised up by 4. So now if we vary x and we want to minimize on the blue curve, right? We use the same thing. We say x n plus 1 equal to x n plus some learning rate times the derivative of z with respect to x at the previous, and now we'd be minimizing along this blue here. Well, instead of fixing one variable and varying the other, we can do this all together at the same time. Like if we are like here and here at the same time, we can take a step in the direction of the gradient, which is the vector partial derivative. So like here, like if that was my x and if that was my initial y guess, and maybe this was my initial x guess, here, right there, that's the vector x naught, y naught. And then we would simultaneously do these two updates. So if we put that in vector notation, so this is like xn plus 1, yn plus 1. That's going to be equal to xn, yn minus alpha times the vector of the partial derivatives. So evaluated at the previous terms. So we can do that in one go, and whichever way along here the x would adjust, and whichever way along this way the y would adjust at the same time. So maybe we're there and then we move right there. Because then x would go this way, maybe y would go that way. Okay, so then if we put all these curves together in space, we have that bowl, and we start descending down the bowl. So let's go ahead and look at numerically what that would look like for this function. Okay. Let's see if we can find the minimizer of this multivariable function. So I'm going to share my screen again. Okay, so now I'm going to say f of x comma y, return x, what is it, minus 1.0 all squared plus y plus 1.0 all squared. Okay, and then, so how can we do this? Actually, I want to just put in a vector instead of having two variables like that. No, we can just do two variables and it'll be easier to see. Okay, so here's the gradient. So grad f for x and y. So return, how do I want to do this? He got arrays, make an array. And in the first entry is going to be 2 times x minus 1.0. And then the second entry, 2 times y plus 1.0. That's the gradient. Okay, so let's make a guess, I suppose. So, array. Let's guess like maybe 10.0 negative 6.0 or something like that. Okay, so let's say a for loop for placeholder and range, maybe let's do it like 20 times. What do I want to do? So I'm going to put that in a list and do the same thing. So old vec equals to whatever I put in there last there, and then new vec equals old vec minus alpha times grad f. And now since it puts in x and y, so I have to do old vec 0, old vec 1. And that's the x value and the y value. So after I do that, I'm going to throw that into x. Okay. So where did it go? Interesting. Maybe I need to go more times. Oh yeah, it's moving, just moving very slow. So what do you think I should do? I should probably increase my step size. It's moving very slow. So I'm gonna make alpha equal to 0.6 maybe. Yeah. See what happens when I increase my step size? I got to the minimizer like immediately. Okay. So that is how gradient descent works. Okay. And you can visualize these things, but it's just a little bit more difficult. So maybe contour plot. Oh, spelled it wrong too. So you put in that and then you put in Z. Okay. Okay, so I'm gonna try this. I don't do this often because this visualizing isn't, no, just for these things, these types of functions, I just don't do it often. It's annoying. Okay, so X and Y. So I need to make an X and a Y. So, oh, I can just throw in the domains I made earlier. Domain, and then throw in domain again. And then now you make a Z, which is going to be F of how can I oh yeah, this is there's got to be a better way to do this. Hold on. This looks like a plan right here. Okay, come back here. Equals. This is just annoying. Oh, I'm plotting. Yeah, so I think that's one way to get around it. Let's see. Let me look up a sample plot. Okay. Looking. Yeah, that looks nice. How did they do that? Interesting. Oh, they multiply all of them at one time. Okay. So I can definitely mimic that. Okay. Come back here. And this is my little y, 0, all that. I don't need any of that. I don't need any of that. This is like my z. Okay. Cut that out. There. See, this is like why I'm like, oh, it's just not worth the time. Not worth the time. But maybe it might be worth it. And then just try this. No. Should be main little while. What did they import? See, this is why it's annoying. And if this doesn't work, I'm just going to say that numerically we saw that. Oh. Okay, well, that did work. So now what I want to do is I want to show those values here. So I'm going to iterate this maybe 50 times. And then I want to so oh, did not mean to do that. So once that's in there, now I just want to scatter the points. So 3D scatter plot. And it's just scatter. Okay. Let's see. So we want to scatter X. And not just X, I want you to scatter F of X0, X1, or X and capital X. Maybe that'll work. Well, in any case, well, I'll spend some time on this after class and make a nice notebook, and I'll post it to Blackboard. But generally speaking, though, that idea, are y'all okay with this idea?
Yeah, I'm following along.
Okay. So in general, of course, we can have functions of n variables, right? So I should probably write that down as well. So in general, we just have, so the general form is X. So your new vector, old vector minus alpha times the gradient of your old vector. And that's what we just arrived at. And this is a really important algorithm for a practicing data scientist. And also, I think a good place to stop this recording and then pick up another recording in a moment.